München, so LMU Munich. Professor Friztsch has a very illustrious career, starting very young in a very special sense. He received his, well, he grew up in, at that time, East Germany, and he received his diploma, it's like a master's degree, at the University of Leipzig in 1968. But about that time, I think the city government actually blew up a 1700-year-old church for their purpose. And Harald, as a young person at that time, had the courage, daring, and cunning to show some sign of resistance. But for that matter, he then had to escape out from East Germany. So that's a very interesting story. I think I put it in his bio that he has a book, Escape from Leipzig, 1968. Okay. So he actually went to Bulgaria by train, I think, and then took a boat for 300 kilometers across the Black Sea to Turkey. And with that kind of daring and determination, he received his PhD from Technical University of Munich in 1971. But in 1970, he already went towards Stanford. At that time, 1970 was a very heady time at SLAC because of discovery of deep lattice scattering. So as a student, he got a student fellowship to go there for half a year at the invitation of Björkan himself. And on his way over, he stopped by Aspen and had a very interesting chance encounter with Murray Gell-Mann, the Nobel laureate. And through that, half of his time at SLAC he already spent at Caltech. And I heard at lunch today, Gell-Mann forced Professor Friztsch and arranged for Professor Friztsch, I'm slipping tongues again, to go to CERN with a CERN fellowship as a student, unprecedented. Okay? So he spent a year or so at CERN, even before his starting even before his PhD and after receiving it, and started a 6-year collaboration with Gell-Mann, including proposing the SU3 color gauge group in 1972. Again, those were very heady days, so at least the color gauge group was proposed by Professor Friztsch and Gell-Mann. He went on to suggest quite a few things. For instance, SO10 as a possible grandification group. I think a lot of his work is related to his talk today about quark masses and mixings and so on. He's a member of the Berlin Brandenburg Academy and has contributed a lot, including the reconstruction of Eastern Germany. And last but probably foremost, he's a proponent of general education in science, written I think of order 10 or a dozen books on popular science. You can easily find him on Amazon and so on. So we have a very fascinating title, and I'll invite you to the floor, Professor Friztsch.
So thank you very much. This is a colloquium on fundamental constants. You're all familiar with fundamental constants in physics, and in particular about a possible time variation. Now, fundamental constants are everywhere in physics, not only in particle physics or nuclear physics, or in solid state physics or atomic physics, even in astrophysics and in cosmology. The first fundamental constant, which you all know, goes back to Isaac Newton. It was already introduced in 1686, usually called G, the gravity constant. And this is a book of Newton called Principia Mathematica in Latin, was published 1685 or 86. And in this book, Newton describes the gravity attraction between two bodies. And as you know, this is given by the product of the masses divided by the distance squared, multiplied with the fundamental constant g. And this describes the gravitational attraction between two bodies. Newton was even able to make the first measurements to determine how big g is. Of course, it's a very small number, but he got the first idea. Now we know the constant g quite well, not too well, however. This is in standard units, like kilogram and meter a second. Now this is the first basic constant ever introduced in physics. The second constant was introduced by Thomson in England in 1897 in a way, because Thomson discovered the electrons studying cathode rays, and he was also able to make the first measurement on the mass of the electron. Of course, now we know it very well. It's about half an MeV. That's the second basic constant ever introduced. And the third one was introduced in Munich by Arnold Sommerfeld in 1916. It is now called the fine structure constant. It's given by the electric charge squared, E squared, divided by Planck's constant, E, H, and the speed of light, C. Now the speed of light and Planck's constant I do not regard as a basic constant. Because you can always choose your units of space and time in such a way that C can be put equal to 1. Just measure the time also in distances. And also you can use the unit in such a way that H is equal to 1. So the fine structure constant is essentially just the square of the electric charge. This constant was introduced in 1916, and 3 years later was a big meeting, the big Solvay conference in Brussels, where the leading physicists came in order to discuss the fine structure constant. You see this group, Arnold Sommerfeld is standing here, he was relatively small. The other people here are Max Planck, you see in the back. This is Lorentz, Professor in Leiden. This is Marie Curie. This is Ernest Rutherford, Henri Poincaré. And of course here you see the young Albert Einstein. Now the atoms in physics are described, as you know, in a simple way. There is a nucleus here surrounded by electrons. The nucleus has a positive charge. The electrons have a negative charge. And the atoms are described very well now in theory by the theory of quantum electrodynamics. That theory was introduced in 1935 by Werner Heisenberg and Wolfgang Pauli. Heisenberg and Pauli described the interaction in such a way that you just have this is the electronic wave function, called the Dirac wave function, usually called psi. And out of this psi you make a current, and that current is multiplied with the electromagnetic potential. And this is the interaction of quantum electrodynamics. It's usually called a minimal interaction for a particular theoretical reason. Now, what Heisenberg and Pauli did was essentially to introduce the first gauge theory. That there is a new symmetry in that theory was at that time realized by Hermann Weyl. And for that reason we call that theory now QED, quantum electrodynamics. The first gauge theory introduced, and as you perhaps know, all the fundamental interactions in physics are now described by gauge theories, except the gravitational theory. the gravitational interaction. And quantum electrodynamics has a symmetry which is based on what is called a gauge group. Now this gauge group is a very simple group. It's a group U1. If you don't know what a U1 group is, it's just you take e to the I, and alpha is a real parameter, which then depends on space and time, and take all possible numbers and they form a group because you can multiply these numbers, and there is an inverse of these numbers, so they have a group, the usual property of a group. Now, based on this, the electromagnetic theory is just a simple interaction of the electron with electromagnetic potential given by this wavy line. But in the quantum theory, the potential is also described by a particle. And that particle is called the photon. It's just the particle which is also light. So the light particle is electromagnetic, makes an electromagnetic interaction with the electron. The fine structure constant is nothing just you take this coupling constant called E, the electric charge, square it divided by 4 pi. In this equation I already said the Planck's constant and the speed of light equal to 1. So this is 1 over 137 as it turned out from the measurements. People were very surprised because this is a dimensionless quantity. Doesn't have any units, not written in terms of kilogram or meter and seconds. It's just a dimensionless quantity. It is very close to the inverse of 137. But 137 is a prime number. So a lot of mathematicians and physicists were starting now to derive this number, to calculate that number. But until today, we had no success in this. The fine structure constant, if I put it in Planck's constant, the speed of light, you see it brings together through that equation the electrodynamics theory related to E, relativity theory related to the speed of light, and quantum theory related to Planck's constant H. Wolfgang Pauli was one of those who tried throughout his life to calculate that number based on a theory, but he couldn't succeed. Even today, we cannot calculate this number, but we can measure it with very high precision. In 1958, Wolfgang Pauli died in the Kantonsspital in the hospital in Zurich. But then it was discovered by Victor Weisskopf, who visited him just before he died, that he was dying in the room number 137. It's a very funny accident. Probably it's not an accident. I think Pauli probably had arranged it. But still, we still don't know why it is 137. Now, the quantum electrodynamics is a theory based just on 2 fundamental constants. This is the fine structure constant alpha and the mass of the electron. Alpha is dimensionless. The mass of the electron, of course, depends on your unit, like half an MeV. In 1964, electrodynamics was increased to the electroweak gauge theory. It was done by Sheldon Glashow, Abdus Salam, together with John Ward, a physicist from Australia, and Stephen Weinberg. Done between 1964 by Salam and Ward and by Glashow, 1967 by Weinberg, 1968 again by Salam. And this theory is now based on a gauge group which is much more complicated than the gauge group U1 for electromagnetism. It's the group SU2 times U1. And the gauge group SU2 describes the weak interactions. And this is U1 describes the electromagnetic interaction, but not completely. There is a mixing between the neutral component of the SU2 and the U1. And as a result, There is now the photon coming describing electromagnetism. There's also a new kind of weak interaction based on the neutral current. And this neutral current had the B side, had been predicted in particular by Stephen Weinberg, and people couldn't find it until 1972, when it was finally discovered at CERN. And after this discovery, it was clear that the theory is at least close to the real theory. And that theory has 4 gauge bosons. The 2 charged ones, a neutral boson, and the photon. So when sorry, it was wrong now. Sorry, I made a mistake. I'll go on now. I have to go through again. So there are 4 of these gauge bosons. And now it happens as follows. Here in SE2 there are the two charged weak bosons. And there is a neutral massive boson. This mixes with the photon. But one mass eigenstate is the Z boson describing the neutral current. And the other one is the photon, which is massless. So there are these 4 gauge bosons. And these 4 gauge bosons were theoretically introduced, but they were discovered in 1983 at CERN. Now in the electroweak theory, we describe everything by 5 constants in the simplest theory. First, the mass of the weak bosons, the W plus and W minus, which have equal masses. Then there are 2 coupling constants. And then there is electron mass, and there is also a neutrino related to the electron. But the neutrino is kept massless. It doesn't have any mass. But I have here one more parameter, the mass of the so-called Higgs boson. We still don't know whether that exists. Peter Higgs and others had introduced this boson already in 1964. And it was used by Weinberg in order to produce the masses for the weak bosons. So in the simplest theory, the weak bosons masses are introduced by using this Higgs boson. But in that theory, you would expect, besides the weak boson, that there is also a new scalar boson called the Higgs boson. And it might have been discovered, but this is not clear yet, 2 years ago at CERN. And I will come back later to this. Now, a few remarks about the strong interactions. For a long time, it was unclear how the strong interactions are described. But then in 1964, Murray Gell-Mann and also his student Zweig introduced new constituents for the proton, which we now call quarks. The name was introduced by Gell-Mann. Zweig at that time had a different name. He worked at CERN, but he did it independently. And in the quark model, the proton now consists of 3 quarks, and you need 2 types of quarks, the up and the down quarks. And there are 2 up quarks and 1 down quark making the proton. In the neutron, things are just reversed. There are 2 down quarks and 1 up quark. That's the internal structure of the proton. And 3 years later, in 1971 finally, or many years later, the so-called color quantum number was introduced, in which we describe now the quarks as a red, a green, and a blue quark. There are 3 different colors of the quarks. And you need this in order to describe certain anomalies in the quark model. And there is a new symmetry curve, which is, because there are 3 colors, which is called SU3 of color. So in the proton now, you have 2 up quarks and a down quark, but the 2 up quarks, either one is red, the other one is green, and the other one is blue. So you need in the proton always the 3 colors together. You could not have 2 red quarks and 1 green quark and not any blue quark. All the 3 colors are needed. And so in other words, the hadrons, like the protons, consist of the three colors. And as you might know from optics, if you rotate these three colors very quickly, you get white. The colors, they average out. So the hadrons could be called as white states. You do not have any color. This is true for all the hadrons, including also for example, for the pi meson. 1 year later, Gaiman and myself introduced a new theory which we called later on quantum chromodynamics. Sorry, I used here for a mistake, it's a German name, I should have used the English name. Quantum chromodynamics, QCD with red, green and blue written. And in that theory, the color group SU3 is then used as a gauge group. We introduced that theory when we were together working at CERN in the summer of 1972. And as you see now, in a proton, the two up quarks and the down quark are now glued together through the gauge bosons of QCD. In quantum electrodynamics, you have one gauge boson, the photon. In QCD, you have 8 gauge bosons, which are again massless. They form an octet of the group SC3, so there are 8 such things. And they are exchanged between the quarks, and now they bind the quarks together to form a white state. In other words, a proton. Now in that theory, you can calculate various things, many things actually. In particular also the mass of the proton. The mass of the proton is just given by the field energy coming from the gluons, mostly the gluons, but also a little bit from the quarks. And this is described, in reality actually, the gluonic field energy makes 70% of the proton mass, and the quark field energy makes 30%. So if the quark masses are 0, the proton mass can now be calculated. It's just a constant which can be calculated using computers, for example. This constant is close to 3, and times, however, a scale parameter of QCD called lambda sub c. And this lambda sub c is a fundamental parameter of QCD which we have to take from experiment. There is no way to calculate this. Numerically, it's close to 300 MeV, it's around 250, 270 MeV. So the fundamental constant of QCD is just lambda sub c. And that constant is similar to the fine structure constant of quantum electrodynamics. Just a basic constant which you cannot calculate. But in reality, we don't have only the up and down quarks. There's also a strange quark, which was already known when the Gauss quark model was introduced in '64. And so there are actually Gaiman introduced the 3 quarks, Gaiman and Zweig. But then 10 years later, the charm quark was discovered, a new heavy quark at SLAC. And much later, the heavy bottom quark and the heavy top or truth quark, T. But now we know that there are 6 such quarks in our world. Now the mass of the proton is just given by this QCD term, a constant which can be calculated times lambda c. But then you get 4 other terms, which are relatively small. The up quark's about 21, the down quark about 19 MeV. But there are also strange quarks inside the proton, and strange quarks and antiquarks. And because the mass of the strange quarks is quite a bit larger than the mass of the up and down quarks, it makes about 36 MeV. There's also a purely electromagnetic term, which has been calculated by Feynman a long time ago, which is very close to 2 MeV. So if you sum this all, you get the physical proton mass of 938 MeV. You might wonder, What about the bottom quark, the charm quark, or the top quark that is not inside here? The reason is that these contributions are too small. They are less than 1 MeV, and that I just forgot them. But in reality, the total strong interactions is now described by 7 fundamental parameters. This is the lambda C parameter of QCD. And then there are 6 quark masses. The up quark, the down, the charm, strange, the T and B. The top quark mass is extremely heavy, it's around 170 GeV. So many orders of magnitude larger than the mass of the up quark, which is very light, only around 5 MeV. Anyway, these are these parameters. The lambda C is the natural parameter of QCD. Where the quark masses are, how they are generated, we still don't know until today. It's still a mystery why these quark masses come in. But now in 1973, after the introduction of QCD and the neutral current and the electroweak gauge theory, we now speak about, in the particle physics, about the standard model. It's based on the gauge group SU3 for color, and SU2 times U of 1 for the electroweak gauge theory. That's now the standard model, based on the 6 quarks, up and down, charm and strange, D and B, and 6 electrons. That's the electron, it's associated neutrino. There is a heavy brother of the electron called the muon that has been discovered already in 1937, together with its own neutrino. And there is a new lepton discovered at SLAC in Stanford in 1975, associated with its own neutrino. So 3 neutrinos, 3 charged leptons, which have electric charges 0 and -1. The electric charges of the quarks are very funny. They are non-integral. The up quarks, the charm at the top, have an electric charge 2/3. The down, strange, and B have electric charge -1/3. But the boson consists of 3 quarks, 2 up and 1 down, and the sum of 2/3 plus 2/3 -1/3 is precisely +1 as it's needed for the proton. This is now the standard model we have. And as you see, there are 3 families of leptons and quarks. What we do is we take up and down together with neutrino electrons. These are the lightest particles. We call this one family. And there is a second family and a third family. So up and down, neutrino electron, charm and strange, muon and its neutrino, T and B, the tau lepton and its neutrino. So there are 3 families of leptons and quarks. Very funny. We still don't understand why the number 3 plays such a big role in nature. As you well know, our space has 3 dimensions. The quarks have 3 colors, and there are 3 families. But there could easily be 4 colors, or could be 2 families, could also be more dimensions, but it's known for a long time that our space has 3 dimensions. So why the number 3 comes in so often in nature? It's still unclear. It's again one of these fundamental constants of nature. I discussed this here. This is a picture taken in 1985. At that time, I gave a lecture at the Vatican Academy of Science in Rome. And into my colloquium, which was on cosmology at that time, also the Pope came. This is Johannes Paul II, the Pope who came from Warsaw, not the present Pope. And he got interested in my talk, and after this colloquium, I had a long discussion with the Pope. Here you see the start of this discussion. This is Nino Tsikiki, a professor from Rome. It's myself, that's the Pope. And the Pope told me he understands why we have 3 generations or 3 colors of quarks.